Today we are very happy to have Carter to give us a talk about ZK smart contract without the VM circuit bloat. So Carter, if you are ready, you can get started.
Okay, awesome. Yeah, let me share my screen here. Good morning to everyone, and thank you so much for being on here. Let me just really quickly figure this up. Alrighty, can you guys see my screen okay?
Yes.
Okay, fantastic.
Yes.
Yeah. So today I'm going to be discussing a little bit about how we're able on QED to develop smart contracts without having a very large VM circuit. So today's talk, we're going to be talking about ZK smart contracts without the bloat. And the main sort of driving purpose behind this is we want to be able to provide fast, secure, and verifiable computation for all, which means obviously we need to solve some of the core, existing problems with blockchain, and we want to be able to offer with our ZK native development experience, obviously, all of the amazing dev tools and familiar languages that Web2 developers are already well acquainted with. And at the same time, we want to have a state model that's very scalable, and we want to be able to allow for local proving so that we can also offer a Web2 like user experience where we have, free and instant transactions that are proved locally. So in order to do that, we compile JavaScript and Python directly to like zero-knowledge circuits. We can go through a little bit of a demo in a little bit, but and then at the same time, we want to be able to offer no compromises on security or user experience. So ideally, we want to be able to allow users to prove their transactions locally, as many as they perhaps like, and only pay a fixed gas fee. And then also on the scalability end, which we won't go into too much today, but we'll touch on a little bit. We want to be able to offer a fully horizontally scalable solution for our developers. But yeah, if we look a little bit at existing ZK VMs, they have very large circuits, and in general, the languages that they support are also either novel languages that no one knows how to write, like everyone kind of knows like Cairo. There's not a whole lot of developers that are writing Cairo or Move. Solidity slightly more, but still not as many as your traditional languages, right? And then on the TPS side, recently there's been that big Starkware, massive posting. What do they have? The emoji with the hands, crossed together or something. But they're celebrating over 30 TPS, right? We all know that this is not really sufficient to hold up for any real use cases like blockchain gaming or dynamic NFTs or DeFi at scale, right? Platforms like Alipay are processing, like 550K TPS or something. So yeah, we have the same poor UX as well. So we need like a better solution than these standard ZK VMs, just because the circuits, they run in serial, they're massive circuits. It needs to be ran on a server because like you really need a lot of resources, when you have these very, very, very large circuits. So we compile standard JS and Python, as I mentioned, to zero-knowledge circuits. And because of that, we have like standard compatibility with any tools that support vanilla ES6 JavaScript, for example. And that at the same time, we want to offer a no learning curve experience for Web2 developers, so they don't have to learn anything new in order to develop.
So quick question.
Yep.
For compiling JavaScript and also Python, is compiling all the features, like for example?
No, so we only support deterministic features. So I guess the best way to understand that is that we offer all the standard library functions except those which are non-deterministic, like math.random. And also we don't have strings currently. So you can console.log stuff. Like I can use strings in like that one function or console.error warn, or you can throw errors, but other than that, you can't use strings. So these are the two current limitations. But in general, like all of the functions that you would want to perform in a smart contract, we support. So we can look at some examples of actual contracts.
Yeah,
but
for example, like system call or like IOs,
we do not.
like
No
memory management.
Well, in JavaScript, you don't really have memory management as part of the standard. I mean, there are like Internet Explorer allows you to like do garbage collection stuff, but for JavaScript, it's like, think of the web browser subset. This is not like Node.js running. It's a ES6 JavaScript runtime. It's not a Node.js JavaScript runtime. So like you get all of your, like you could do like let's say like iterator mappings, like I could do like .map, .for each, all of those kinds of things. I can take advantage of things like inline functions and all of that good stuff. So it's you still get a lot of the features of modern JavaScript, specifically everything in ES6 that's deterministic except for strings. Yeah, so you can imagine that the way that we actually accomplish this has to do, I guess maybe I shouldn't say too much about this, but you can there is already quite a lot of existing JavaScript tooling around building JavaScript ASTs. Like everyone knows Babel, right? So it's not too difficult to do these kinds of things with mature languages that have like a lot of support, because essentially we just need to do a symbolic evaluation for the program, noting areas where we have things like ifs and fors and whiles where we have conditional constraints to be added. And then the basic like sort of gist of things is that we want to do a symbolic evaluation of the JavaScript program, although it's not as simple as that, because again, you have like, let's say you have a for loop, which has a body that, I don't know, maybe it has its iteration count is a function of the inputs to the circuit. So in that case, you either need to do to like vectorize. So you try to vectorize the constraints. If you can't vectorize the constraints, then you need to do like certain permutations. And we'll talk about a little bit how that works. And then worst case scenario, you can always fall back to recursive proof verification. But yeah, so we can see some of the features like on offer. So like over here, you can see like we have like incrementing a variable count by a, an object property name. We also allow like dynamic typing. So it's like, it's very plain Jane vanilla JavaScript, right? In this case, TypeScript. Yeah, and we have like a nice full debugger. And the reason why we have a debugger that looks so nice and works so nice is just because, again, it is plain Jane vanilla JavaScript. Yeah, you can see we can use strings like essentially like if there's any Rust developers in the crowd, the sort of rule of thumb is like @str is okay, but we don't have string, right? So you can put in constant strings that are used for things like over here where we have inc variable account or this dot require, but the actual like values of characters and strings, we don't support manipulation of those or creation of strings. So it's like it's there for you if you want it for debugging purposes or for logging purposes, no problem. But yeah, so in the circuit we don't support like manipulation or storage of strings. Let me really quickly just zoom on back here so we can talk a little bit about the ABI. So I'm not sure how good the resolution of my video stream is. 就是我目前在法国，所以我不知道就是国内的这种腾讯这个平台会不会大家能看到吗？我不知道够不够清楚，就是可以看一下这个 ABI。
没有问题。
可以。
Okay, cool. So yeah, so we have this like ABI format. It's called DAPN, and it essentially allows us to specify for our contract what the different contract functions will be. So you can imagine as an ABI, we want to have a unified interface for JavaScript, Python, and in the future more contracts, just so that there's like extreme interoperability between contracts. And it also allows us to define the memory storage mapping for our contract. I can jump over a little bit so we can see kind of what that looks like. So yeah, maybe I can just, yeah, so we can see that the way that this is, by the way, so this is a state diagram for QED. So we have these contract function trees, and essentially what we do is we compile the sorry, jumping around too much. So we compile these JavaScript functions in a contract, each individually to a zero knowledge circuit. And then we make a Merkle tree with the various circuits verifier data in the leaves of that Merkle tree. And then what we can do from there is whenever we are locally proving, we first generate a zero knowledge proof according to the circuit that we compiled for that specific contract. And then we have a cyclic recursive local proving, what we call a user session proof. And that's going to recursively verify the contract function circuit proof that was generated by using the circuit that was deployed by the contract deployer. And we do a recursive verification as well as a Merkle proof, which links the circuit that's being verified directly to one of these contract function trees, which corresponds to the contract that you're proving for. And then we guarantee that the verifier data for that circuit is within that Merkle tree. So that way we're able to guarantee that for any given contract's state Merkle tree, the only circuits that are allowed to update that tree or are allowed to, I guess, authorize updates to that tree is probably a more accurate way to say it, are within that contract function tree's Merkle leaves. So if we look just really briefly at like what a contract function circuit is going to be able to, or has as public inputs, these are actually not the public inputs. We do a hash of these values, and so that way we only have 4 public inputs. We use a very small field size, but you can see some of the things that a contract function circuit is able to expose. So we have the block ID or checkpoint ID, the hash of the checkpoint. So basically information about the entire state of the blockchain when this contract is being called, a user state trees hash, and so on and so forth. And we use this to essentially provide the contract function circuit access to the global state of the blockchain. And then in addition, we have these transaction and concurrent proof debt hash stacks, and that essentially allows us to make deferred transactions to other contracts, since a given contract function circuit only is able to update its own state tree. We don't allow for things like reentrancy. This is also for security reasons, but essentially we still want to be able to allow different contract functions to be able to make external calls. So of course we have to preserve usability, but without sacrificing security. So we also allow you to essentially, when you have a recursive verification of a contract function circuit proof, you can, in those public inputs of that contract function circuit, also add this proof debt or proofs that need to be added, which amount to calling other transactions on other contracts. And in order for you to submit a local proving session, so a bunch of these recursively generated proofs of all of the transactions you've made, that proof debt hash stack needs to be cleared. And the only way to do that is to also execute the transactions that are required by that contract function. So yeah, we're able to, this also gives us the benefit of parallelizing, because we actually run the contract function circuit for witness generation. We run it in our own VM. So again, we have a VM that generates our witness, but we don't have to check the VM bytecode in a large circuit. We just have a specific circuit that generates that is like the minimal constraints for some verifying the execution of a given program. But yeah, so like here we can see just one sort of contract function circuit's logic. But yeah, for the cycle circuit, as I mentioned, it's just recursively verifying a bunch of the contract function circuit proofs, and essentially it maintains a state tree for a given user. And when it takes in a contract function circuit proof, it's going to update the state tree via delta Merkle proof for a given contract, and also resolve different calls to that linear proof debt hash stack. So you can imagine a contract function comes in. It's a little bit similar to having a call stack, where every time you want to make a function call, you can push to the call stack. However, we have it so that we don't have to do recursive proof verifications within a contract function circuit. And also, since we are a ZK native chain, we allow you essentially to provide whatever kind of valid zero knowledge circuits verifier data that you want in your contract function tree. So it's by definition untrustable. It's only trusted to update the contract function tree of where the index is equivalent to itself. So if we have a contract function tree with contract ID 0, let's say. So this is the Merkle tree that contains all of the verifier data for the zero knowledge circuits that are allowed to authorize updates to the contract state tree with ID 1. And then for each given user, we'll have a bunch of different contract state trees, one for each contract. And then this contract will have a bunch of different function circuits which are able to update or authorize updates to that contract state tree's Merkle root. So basically you give it a start and an end, and it's able to generate a proof that that transition from start to end was valid. But yeah, so the benefits of this are myriad. There's really a lot of ways that this just makes more sense. Proving time is 1 digit milliseconds. Recursive verification right now takes about 80 milliseconds, but it's just a lot faster and a lot less resource intensive than using a large VM circuit, just because with large VM circuit, you have to implement every opcode. It's going to be pretty big. And then, the number of steps that you have usually is quite large, because usually if we look at, for instance, Starkware, their VM has 3 registers. So you can imagine, yeah, there's a lot of instructions, and each instruction could be one of many. So we have a lot of permutations. It just gets very icky. The other good thing is because we have a wonderful, because we have a wonderful Merkle tree with all of our contract function circuits, we can also do permutations where we have an optimized case. Let's say, I don't know, you have a for loop, and I want to generate a circuit where the condition in the for loop is such that it has 2 iterations. I can generate a circuit which has that requirement and put it in the contract function tree. I can also generate another circuit where it has 3 permutations, or where it has 3 iterations, right? And I can generate lots of permutations of the circuit so that we don't have to deal with too much branching within our logic. And then, of course, if we want to deal with branching, we can always just have constraints where we multiply by 0 on both sides if some condition is not met. So essentially, we use that along with some simplifiers like C3 to generate an accurate symbolic trace of the program. Yeah, it usually tends to be about for a reasonable size smart contract function, something I don't know, 800 vector constraints. So what that translates to into the actual polynomial constraints, maybe a little bit more than that, but yeah, still significantly smaller than the millions that you would see with a ZK VM.
So just to understand this,
Sure.
the tree. So for the previous slides, so this is kind of a Merkle tree for all the including all the historical data information, or just one.
This checkpoint tree does, yes, but one checkpoint stores the current state. We allow access. Okay, yeah.
Yep.
So one very interesting thing is about our state model is that we don't require you to be linked up to the latest checkpoint or the latest block to be locally proving, because all you have to prove And this is maybe I could tell everyone about it. I mean, we're going to be announcing it soon anyways. Yeah, so basically you need to prove that the checkpoint that you're on is greater than or equal to your last checkpoint ID, right? So you can't go backwards, but you can stay where you are if you like. So this allows you to fetch data from nodes that aren't synced up with the entire state of the blockchain. And also we do extreme fragmentation for all of these trees and which nodes are incentivized to store which parts of their state trees. We have our own custom Merkle tree database that has ZK friendly Merkle hash, and we also have a zero Merkle tree strategy so that it actually when we do storage, we only have to store deltas. So, and we can always do log n lookups of historical data. So basically you give which checkpoint you want a certain value for any of these Merkle trees from. But yeah, we also allow contracts to query or rather include Merkle proofs that tie to historical data. So I can prove things about the state of the blockchain at a previous state, which is very useful for things like, if you want to have more complex logic, but you don't want your contract's Merkle tree to be too deep. So obviously that reduces the circuit complexity, the number of 2-to-1 hashes that we have to do whenever we're touching a Merkle tree for our contract state tree. But yeah, so all of these are Merkle trees. Do you guys have any other questions? I know it's quite a new thing. It's a different state topology than anyone else has used in the past. But the main idea is that you have this checkpoint tree root at the start of a block, and all of the transactions in the block, or all these transaction proof chains, are going to agree about either the root, or they're going to be on a root which is greater than or equal to the previous checkpoint that they were on. And of course, if we know that the current root of the checkpoint tree is let's say X, and someone is on a previous checkpoint, let's imagine that perhaps this node over here is a 0 on the previous checkpoint, and now it's being updated with a new value. I can always verify that there was a valid previous checkpoint root by just saying, okay, at whichever index they think that the current checkpoint tree, or whatever block number they currently believe the state of the blockchain is, we first do a Merkle proof which links that checkpoint hash or the state of the blockchain at the block that they claim to be on, and guarantee that it's in the current real checkpoint root. And then we also do a Merkle proof where we keep all the siblings where the index of the sibling is a left-hand child, meaning that the Merkle path of the checkpoint that we're looking at is the sibling that in question is resultant from a previous checkpoint, so it should be a non-zero one. And then if it is a right-hand sibling, then we, instead of using the current sibling from our current checkpoint proof, we use a 0 Merkle hash. So the 0 Merkle hashes are going to be 0 for the leaves, the hash of 0 and 0 for the level above that, the hash of the level below that, and the level below that to get the other one, and so on and so forth. And we use the 0 Merkle hash, and then we can simulate what it would look like for that tree at that given point in time, where all the leaves to the right are going to be 0. And then we can make sure that the root that they claim to have is therefore both included in the tree's history, and also that value exists in the current checkpoint tree. So yeah, so we don't even require people to be synced up to the latest head, which is really nice, because you don't want to always have too much data flowing between the user and your network, just because we want to make it as inexpensive as possible for our different partners and nodes to provide reliable infrastructure for as many people as possible. Yeah.
Another question is how to define the state transition in this model. So for example,
Delta Merkle proofs.
Sorry?
Delta Merkle proofs.
Okay, Delta Merkle proofs that in the format like key value or some structure.
Yeah, so when we submit to the server, like, okay, so for the actual circuit, it's like value or new value, old value, new root, old root, siblings, right? This is an index, right? This is a Delta Merkle proof. So we have a compact form of that. So like for instance, if you do like sequential ones, we don't like, so of course, like how do I put this? Let's say I update like 8 values that are with index, I don't know, like 0, 1, 2, 3, to 8, right? The most efficient way for me to have a node, because we have the nodes like when you submit the API request containing your proof, it also tries to make sure that or it also does make sure that the data that you're sending reflects the Merkle root changes that are, you know, inside the public inputs of your zero knowledge proof. So we send like these sort of like batched, like you can imagine, we essentially send like a range of indexes and then leaves, and then we send the siblings when it makes sense to send the siblings. So like you can, let's say, prove to a certain depth, and then at a certain depth you just provide the leaves, because you're going to need to like rehash that part of the Merkle tree anyway, since you're updating all of the leaves in a section, because it's like basically like we round down to the lowest power of 2 and then provide the leaves, and then anything above that we provide the siblings and the new and the old root, if that makes sense. So we have like our own like proto buff, like compact, like batch Merkle proof, or batch Delta Merkle proof, we refer to it as format for doing that. But yeah, it's it like what actually happens is that we map that to a Merkle proof. So yeah, what is sent over the wire though is more compressed. I hope that answers your question. We'll be releasing like some API documentation over the coming weeks, and that should make this clearer. I know it's like also it's very difficult to explain in a very short period of time, because there are a lot of significant changes that we've made. Like none of this is really gonna feel very familiar, which is unfortunate, but it's kind of necessary to build this kind of a blockchain at scale. But the main thing is like, you know, whenever we have these circuits that are, oops, sorry, I have to jump around too much in this PowerPoint. We just made some of these things public, so this is like the first time. This used to be an internal PowerPoint, so yeah. But the main thing is like within our proof system, we're just making sure that whatever checkpoint hash we're on, that we can tie all of the assumptions that are made by the contract function circuit about the world to the current checkpoint that we're on, so that we have this chain where the only assumption for each of these proofs in the chain is that the current checkpoint hash is something, and then we can aggregate them in parallel, and then we just make sure they all agree about the current checkpoint hash, and then we do a recursive verification of the previous block and make sure that the start state that proof had is the same as the start state that everyone agreed upon. And then after that, we do that recursive verification, we generate a proof, and we have a new state for the whole blockchain, right? So yeah. Any other questions? No?
Can you hear me?
不知道各位有没有什么其他的问题？用中文也可以。
Hello, can you hear me?
哦，可以啊。Yeah, I can.
Yeah, so one quick question. So the checkpoint tree, is it for the whole blockchain or for one block?
For the whole blockchain. So each block is one checkpoint. So you can imagine,
It's
I don't
one
know,
leaf,
can I
right?
draw on the screen? I think I can with 腾讯会议，好像可以。Maybe not. But yeah, I don't know. Can you see my cursor?
Yes, I can see.
So 一个区块就是这么多的数据，所以就是每一个区块都在这个 Merkle 树。 So the checkpoint tree is for the whole blockchain, but we allow a given checkpoint to know what the current checkpoint Merkle tree root is when we're building. Like, so let's say we're building the third block, right? So it knows, the third block knows about the checkpoint root where this leaf is 0, but these 2 leaves are populated by the first and the second block. So this allows us to like make sure that people don't have to be synced up to the latest again, because we have like a different state segmentation or state isolation strategy where we allow for global state, meaning that I can query any other user contract tree or contract state tree at the current block that I'm on, but I can't affect, transactions that they make, which means that we can process things in parallel because there's guaranteed to be no race conditions. And we can do historical data. This is also useful for some of our like fully homomorphic encryption strategies, because you need to be able to do non-repudiation where you can guarantee that, let's say we use some key to encrypt data that's proved locally, and we're storing some like encrypted data inside of the contract state tree of a contract. We need to make sure that when that data is used in the future, that the key which is used to decrypt it, because usually we're using symmetric encryption for these kinds of data because it needs to be fast. We need to make sure that the key that the encryption or the decryption key is actually the same encryption key that we use to encrypt the data in the first place. So we have like in-circuit KDF that allows us to have reference a specific checkpoint and prove that data was updated at a specific block, because that the key derivation function for encryption of a specific leaf in a specific tree at a given checkpoint, part of the KDF is reliant on the checkpoint number. So in that way, we're able to have non-repudiation as well. So yeah, historical state is just useful to access. We don't require all nodes to keep full historical state. We require them to keep the latest 5 blocks. So there isn't currently a full history requirement, but of course we incentivize nodes in other ways, because like users can pay for very old historical data. A lot of chains like in the past that have very high throughput have struggled with like keeping full historical state of the chain. And yeah, we're working on a lot of strategies. I wouldn't say it's like a solved problem, but yeah, we're trying to make it as lucrative as possible for people to keep full blockchain state.
Okay. Sorry, I think it's a little bit too far from what I'm thinking, but so I understand like each leaf in the checkpoint tree is kind of block, and I think what you meant is like kind of proof is like proving like you have a previous checkpoint and now you are making a valid transfer from that state to a new state, and then you can put it on a checkpoint tree. So it's that
right, and that is equivalent to a block. So this process, so basically like this UConn and C state, these are being proved locally, and the rest of these are being proved by our decentralized proving network.
So most of these, so like the subtrees in these pictures are, maybe I can say 80% are not changed for like each block. So like from previous block to
because there's different. So I want to be clear, like they usually, well, if there's a contract function deployment, then the global contract tree gets updated. If someone submits an event on a layer 1 that we support to layer 2, then the external chain tree is updated. But I would say that the like 99% of the leaves in a given block, well, again, it depends how many people submit proofs to the block, right? It just depends on how many actions occur.
Yeah, how many transactions.
But we store the Merkle trees. You can imagine we have like basically, I can just spell this out, like this is no real big secret, but you can imagine we have like a key value store, and for the key we put like the index of an item within a Merkle tree, which Merkle tree it's in, the level of the Merkle tree it's in, the index, and then at the very front of the key, so the thing that's gonna be the key like sorting determinator, is the checkpoint ID that value was updated in. And then we just have a key value store like that. And then whenever we want to fetch a Merkle proof, we can fetch any node, and we just like say the checkpoint ID must be greater than or equal to, or rather, we want the most recent checkpoint ID like key for some, you know, index in the tree, if that makes sense. So the like based on that sorting paradigm, you know, we still get like log 2 or log base 2 of n lookups for a given block. But yeah, so doesn't matter
example,
that we don't
I
have to
think-
store like the full state over and over again. It's like if we update, like let's say 10 leaves, the like storage expense of that block is like 320 bytes.
For example, if there has no transactions that deploy in your contract, I can say the gcon and cfunc trees will not be changed, right? So you are just calling like.
Oh, gcon tree is append only. It only gets updated one time. So the gcon tree only gets updated when you deploy a contract.
Right. So every time you need to recommit this tree, or you just prove it's the same with the.
No. Once you've updated the tree in the global contract tree, it's so basically like the circuit that we have this concept called parth. We have like parallel ascending like tree hierarchy where, so we have like, you can imagine that there's some checkpoint. Actually, I can just show you. So we have like a checkpoint tree, like the block circuit. So it recursively verifies a proof from a contract function tree aggregation circuit. And that's going to be an append only circuit where we're appending to the global contract tree. And so we do like an append only Merkle proof where we basically guarantee that right side siblings are 0 hashes. So once that's done, this tree, so the tree, like when the block starts, it's not an empty tree. When the block starts, it's the tree from the previous block. Does that make sense?
The previous checkpoint.
Yes.
Okay.
If nothing gets modified, then the new checkpoints like root is or the new checkpoints leaf is going to be same as the previous leaf. I'm just saying that we only store the deltas. Like our database, like our Merkle tree database, is very efficient at storing this kind of like where we would need to have historic availability. We only have to store the deltas. But when you query, you're querying the whole tree. So the tree is mutating. The tree is being transformed at each block. And it's going from A to B to B to C. So if I update a value in, you know, index 0 and then I don't change it in the next block, it's going to have the same value as it was. Or let's say I update a leaf 0 from being 0 to 1,000, right? If I don't modify it in future blocks, it's still going to be 1,000. I think that should make it clear, right?
Probably one question regarding such design. So why is design in this way? Because like most of the, for example, smart contract these days, for example, Ethereum is just access the current state, which in your case is just the
race conditions.
The previous checkpoint. So to address race condition you just mentioned, or what?
Yeah, because we want to process everything in parallel. So we let the users prove their transactions locally, and we want to make sure that we can like, so when we build, you can see like when we build this global user tree, the updates there, we just use like a ZK tree pattern or a like recursive tree, you know, proof verification system to build up that tree, to updates to that tree. So it's done fully in parallel without the risk of any race conditions. So as a user, I can access the state tree. I can read from the state tree of any other user at the start of the previous block or at the start of the current block, right? Which is basically the end state of the previous block. So I can use like that kind of commit pattern. Like for instance, if I want to send tokens to another user, we burn the tokens, and I store something in my contract state tree that says I'm burning these tokens for a different person, and then another person can also use a contract function which looks up to see, hey, this person has burned these tokens for me and now mints them in the next block. So this is like the cost, or I guess the downside is that you have to use scalable web to like state patterns. We also have like MapReduce contract functions that make it easier so that you can build like voting and stuff like that without having to like write too much like crazy logic. And we also have in progress like a full abstraction that for certain different operations that need to be like sequenced. Like you still are using this commit pattern, but the commit pattern is like automatically generated for you using proofdet. So then we guarantee that like the chain as a whole can still remain fully parallelizable and have no chance of race conditions within a given block. Like whenever I submit a transaction, it's guaranteed not to affect the execution of another transaction within the same block. It can affect the execution of transactions in future blocks.
So this requires some kind of asynchronous programming model. Is that correct? Like, for example, I have to suppose suppose a transfer case that will be decoupled into two operations. Like one is to emit basically send a token, which is deduce the value from the sender, and then when the receiver would like to add this value to its account, so basically it will be consist of two transactions rather than right now EVI has one transaction.
Exactly. But the good thing about our chain is that you don't actually pay per transaction because you prove the transactions locally with like a chain of recursive proofs. So you can the gas cost for this is essentially just dependent on like it's constant relative to the number of transactions. It's just a function of the amount of state deltas that you make in a transaction. So yeah, like if it's a balance, then again, you're not really like adding additional state data to the tree, and I can like claim a bunch of different transfers. So yeah.
Okay, got it.
Yep. So it's like this is really the only way if we want to scale up, like we have to adopt like the scalable patterns that are used by like existing databases. Like we also have atomic contract variables that are global, but they're sort of like virtual. And it basically just amounts to a MapReduce on the users of the contract, right? Where we like, sum up, for instance, like the different votes, the different yay votes and different nay votes for all the users. So this is really the only way to scale. We have to adopt as a community, like the well-known Web2 patterns that, avoid these kinds of race conditions that, like when you're using modern databases, atomic operations at scale are necessary, right? So yeah.
I have one question.
Sure.
When you talk about like the users will generate proofs locally, I think you want to say like eventually you can parallelly like aggregate all those proofs to
not eventually. Now.
What do you mean?
It works now. It's done. We already did it.
No, I mean like some kind of a sequencer or aggregator.
No need for sequencing. The order does not matter because transactions in a given block are guaranteed not to affect each other's execution.
Because
when I'm executing contract
functions, but then that will
my
be
contracts can
eventually
only access the state of other users' state trees at the end of the previous block. So they don't know about things that occurred during the current block. The only things that your contract transactions know about the current block are the things that were affected in your user contract tree. So at each level of the tree, you can think of the zero knowledge circuits can be aware of the entire state of the blockchain at the end of the previous block, as well as for each of these, we have a different circuit, right? As well as any of the state trees that are under it. Does that make sense? So you can be aware of the user contract tree or the different contract state trees within your local proving session at the level of these two circuits, because we can know about this without affecting our parallelizability. And the global user tree can know about multiple updates during a different during a given checkpoint or a different block, but we don't allow users to make transactions or for those contracts to read state from the current block number except for their own user account. Does that make sense? So that way we're able to guarantee that there's no chance of transactions within a given block affecting each other's execution.
But what about like a double spending transactions for the previous state, like the last checkpoint?
Oh, well, that doesn't matter. It doesn't affect our parallelizability because that state is already finalized. So everyone already agrees to it, and it's not writable during the current block.
So you mean some transaction will fail even though they...
No transactions will fail. The proving will just fail, cannot fail. I want to be very clear. The previous checkpoint state is already finalized when the new checkpoint is being built, right?
Yes.
We agree on that. Yeah. So if a transaction is able to like view the current state of a given user contract tree, right? So this is a serial, the local proving is a serial process, right? But that end proof is incorporated into the global user tree, the new user root for the user contract tree. When we're assembling that, we can do that in parallel because those user proofs don't make any assumptions about what other users' state trees are during the current block. Does that make sense? It only makes assumptions about
because it's a local process, you don't know.
Which everyone agrees on, so there's no race condition. And there's a constraint which guarantees that everyone agrees on what the previous block state was.
So you mean like the local users tree will be sequenced. So there will be
the local, yes, the updates to these are sequenced because it doesn't matter if we have serial performance at the user level, right? What we want to parallelize, so what we're maximizing here is the number of those end proofs that can be aggregated into the global user tree at once, because that's we want to parallelize the work that's being done by the network, not by the users. Does that make sense?
Sorry, could you repeat again?
We want to parallelize the work being done by the network. So these updates to the user contract tree and set contract state tree are done locally, right? So these are done essentially using a serial process of this. Let me show you. Give me 1 second. I actually have an animation that should make this a little bit clearer. We have some nice animations. But yeah, so do you roughly understand, like, I guess the oops. We can publish this video later if I can't find it. Shit. Yeah, let's see. Shoot. Okay. Yeah, sorry, I can't find the video. But essentially, like for each of these user proving session circuits, we're going to be recursively verifying a previous. That's why we call it like a cyclic circuit group, because we're recursively verifying another circuit proof within that group. So locally, you have a linear, like you're making linear changes to that user contract tree via the user proving session. Does that make sense? So this tree is updated locally, and updates to this tree are made serially. But what we want to do to make the network parallelizable is we want to support as many users as we can submitting proofs within a given block, because a user submitting one proof can have unlimited transactions within it. So a block doesn't have to wait for all the users to finish their transaction, proofs to finish up a block. Like you could submit that last transaction proof whenever you want, because again, you don't have to be on the latest revision of the state. We just have a constraint which checks to make sure that within whenever you submit a proof, that the checkpoint ID that it's on is greater than or equal to your last checkpoint ID.
So may I say, like you're doing something like sharding, like you force the user trees to be splitted and the consistency of each sub-user trees is guaranteed by the prover, so not by the network, the verifier.
Everything is guaranteed by the circuits. So each of these circuits guarantees everything. Like,
yeah,
for
so
instance, the verifier data that's being proved locally of those circuits is verified by the network, right? So there's like a white list, right? So you as a local user, there's a hierarchy of circuits and each guarantees a different thing, but each circuit in the hierarchy also makes sure that the proof that it's verifying has the correct verifier data. So that you didn't change the circuit. So you end up with a single proof which guarantees everything.
So what about transaction like maybe cross those user like sub-user set?
Again, we have like a commit pattern. So you commit to a transaction and then it gets done in the next block. So it takes multiple transactions. This is the only way to scale. But we have a nice abstraction that makes it very easy for people to do.
Okay, now I think it's more clear. Thank you.
Cool. Any other questions? Again, I'm very sorry. Like, there's a lot of new things. It's a new state topology, so we will be publishing like a lot more resources that make it very clear. Like today, we just kind of wanted to announce and kind of like get the debate going, and also we hope that others can see what we're doing in terms of like trying to bring more scalability to blockchain, and local proving is also just good for bringing about a private internet. But we'll have like a lot more resources and diagrams and animations. It takes time to build those, but we'll have a lot of them published very soon. So hopefully that should make it like much more clear. But yeah, I apologize for the sparse documentation that we currently have. Any other questions? And also, if anyone has any questions or 就是有任何问题都可以随时，我们都在 Telegram 或者是 Twitter， 就是一直都在。我们也是希望可以就是多了解就是社区的一些反馈或者是一些想法。反正大家我们就一起建设这个很美好的可扩大的这个 ZK 的未来。Okay, cool. If there's no questions, should we just leave it at that? 不知道，我看一下。
可以看看大家还有什么问题。如果大家想就是说回顾今天的这个视频的话，也欢迎大家去访问我们 Web3BuidlerTech。往期我们所有比如说 ZK 系列的视频都可以在上面找到 link。对，也希望大家去关注我们接下来整个 ZK 系列接下来的一些系列的分享。对。